Hello and welcome to Lecture 5. This week we're going to talk about repeated roots of the characteristic equation, the method of reduction of order, and then we'll move on to talking about non-homogeneous equations. And the first method we'll use for non-homogeneous equations is the method of undetermined coefficients. First, let's do a recap of last week's lesson. To solve a homogeneous second-order linear equations with constant coefficients, we need to find two linearly independent solutions, which we'll call y1 and y2. After we have these two linearly independent solutions, the general solution is a linear combination of these two functions. But what are these two functions? The first thing we do is we solve the characteristic equation. What we do is we take the differential equation and we're going to copy the same numbers. So if the numbers are a, b, and c in the differential equation, our characteristic equation will have the same numbers, a, b, and c. Instead of y double prime, we'll have r squared. Instead of y prime, we'll have r. Instead of y, we'll have 1. Let's suppose we've solved this characteristic equation. We've found the roots r1 and r2. Case 1, if these two roots are both real numbers and they're different real numbers, then the functions that we want are e to the power r1t and e to the power r2t. Case 2, if in fact we have complex numbers, complex conjugates, then we want two different functions. We want e to the power lambda t cos mu t, and we want e to the power lambda t sin mu t. There's a third case which we haven't done yet. What do we do if we have repeated roots? That's the same real number twice. Let's study that now. So we're going to be considering the second order linear homogeneous differential equation, ay double prime plus by prime plus cy is equal to 0. But now, to get repeated roots, we're going to be assuming that b squared minus 4ac is 0. Then the characteristic equation has only one root. We use our usual formula, minus b plus or minus the square root of b squared minus 4ac over 2a. But now, because b squared minus 4ac is equal to 0, it's minus b plus or minus 0 on the top. So we just get minus b over 2a. So we know one solution. We know that e to the power minus bt over 2a is a solution. But to be able to solve a second order equation, we need to have two linearly independent solutions. So how can we find our second solution? We'll start with an example. Solve y double prime plus 4y prime plus 4y is equal to 0. The characteristic equation, r squared plus 4r plus 4 is equal to 0. It's straightforward to see that we have root minus 2. That's the only root we have. r1 and r2 are the same number. Okay, so we know one solution. One solution must be e to the power minus 2t. To be able to write down the general solution, though, we need to find a second solution, and we need that the second solution is linearly independent from this first solution. So the idea is this. We know that y1 is a solution of this differential equation. So we know that if we take y1 and we multiply it by any number c, we also have a solution, because our equation is a linear equation. So the key step here, the guess we're going to make is, maybe instead of putting a constant c in, we could put in some sort of special function. Maybe vt, y1 of t is a solution for some special non-constant function vt, which we don't know yet. So we're going to look at vt multiplied by y1t for some function vt which we don't know yet. So let's differentiate this 2 times just using the product rule. I'm skipping steps here. Of course, when we differentiate it once, we get 2 terms. Differentiate it a second time, we would end up with 4 terms. But 2 of those terms are the same. We can combine these together in the middle term. I'll leave this for you to check. And then I'm going to substitute this into the differential equation. Instead of y2 double prime, I'm putting in the red function, and then plus 4y2 prime, so plus 4 multiplied by the green function, plus 4y2, so plus 4 multiplied by the orange function. Simplify everything down, lots of terms cancel. I have a minus 4v prime and a plus 4v prime. There's also plus 4 minus a plus 4v. These will cancel, and we'll just end up with v double prime e to the power minus 2t. So we have 0 is equal to v double prime e to the power minus 2t. Exponential functions are always not equal to 0. So if this is true, we must have that v double prime is equal to 0. So as long as we have a function v which satisfies v double prime is equal to 0, then we're going to end up with our new solution. V double prime equal to 0 has infinitely many solutions. We just need one solution. We just need one function which satisfies this. One non-constant function, I should specify. So what's the easiest function which has the property that when we differentiate it 2 times, we get 0? The easiest function that I can think of is t. So then y2 is going to be v multiplied by y1. That's t multiplied by e to the power minus 2t. And that should also be a solution of the differential equation. But are these 2 functions linearly independent? To answer this, we need to calculate the Wronskian of y1 and y2. So here we go. The Wronskian is the determinant of this 2 by 2 matrix, y1, y2, y1 prime, y2 prime. Put the functions in, calculate the determinant, and we get e to the power minus 40, which is always non-zero. So the answer is yes. These 2 functions are linearly independent. So that's what we need. We have 2 functions. They're both solutions of the differential equation, and they are linearly independent. So they form a fundamental set of solutions, and we can write that the general solution is c1 e to the power minus 2t plus c2 t e to the power minus 2t. Let's do this again for the general equation. Now let's look at a y double prime plus by prime plus cy is equal to 0, and let's see if the same thing happens. We know we have one solution. We know e to the power minus bt over 2a is a solution of this differential equation. And we're going to do the same guess. We're going to guess that the second solution is vt multiplied by y1. For some function vt we don't know yet. Then what we can do is we can differentiate y2 twice. We can substitute it into the differential equation, and I leave this for you to check. Once we do this, you can check that ay2 double prime plus by2 prime plus cy2 using this y2. You can check that everything simplifies down to a e to the power minus bt over 2a v double prime. Now, the number a is not 0 because we have a second order equation. If a was equal to 0, then we would end up with just a first order equation. We know we don't have that, so a must be non-zero. An exponential function is always not 0. So just as before, we must have that v double prime is equal to 0. So again, we want that v double prime is equal to 0, and we could choose any function which satisfies this. I'll choose the easiest one that I can think of, which is t. So our second solution is going to be t e to the power rt, or t e to the power minus bt over 2a. We should check that the Wronskian of e to the power rt and t e to the power rt is not equal to 0. I'll leave this for you to do. After we found that the Wronskian is not equal to 0, we know that we have a fundamental set of solutions to our differential equation. So here we are. This is what we're going to do. Our two solutions are going to be e to the power rt and t multiplied by e to the power rt. Let's do an example. This time an initial value problem. Solve y double prime minus y prime plus a quarter y is equal to 0 with the initial conditions y of 0 is equal to 2, y prime of 0 is equal to 1/3. I'll explain later why one of these is in red. The first thing we do is we write down the characteristic equation, and we find that we have repeated root 1/2. As soon as we know the repeated root, we can write down the general solution to the differential equation, because we know that the two functions that we want are e to the power rt and t e to the power rt. So the general solution to the differential equation must be constant e to the power rt plus constant t e to the power rt. All that is left to finish this problem is to find the constants c1 and c2. So we differentiate one time, and then we replace t by 0. And straightforward to find that c1 must be 2, and c2 must be minus 2/3. I'm not going to spend time here. I'll leave this for you to check later. So the solution to this initial value problem must be 2 e to the power t over 2 minus 2/3 t e to the power t over 2. Let's do another one. Now solve y double prime minus y prime plus a quarter y is equal to 0 with the initial conditions y of 0 is equal to 2, y prime of 0 is equal to 2. This is the same differential equation that we just looked at in the previous example, and the first initial condition is also the same. But now we have a different second initial condition. I'll leave this one for you to solve. I'm not going to do the details. Please do the same method, and you can check that the solution to this initial value problem is 2 e to the power t over 2 plus t e to the power t over 2. I'm going to show you the graph of this solution, and I'm going to show you the graph of the solution to the previous example. Here they are. Both of these curves are solutions to the differential equation, and they both satisfy y of 0 is equal to 2, because they're both passing through the point 0, 2. If you think back to the previous chapter, I said solutions to first order equations could not intersect. That's not true for second order linear equations. They can intersect, but they can't have the same slope at the point that they intersect at. Now note that these two functions have the same y0 value, and their y prime of 0 value is not that different. One of them has y prime of 0 as a third, and the other one is y prime of 0 is equal to 2. And there's not a big difference between the number 1/3 and the number 2. But the behavior of these two solutions is very different. One of them goes up to plus infinity, and the other one goes down to minus infinity. So let's just do a summary of what we know about second order linear differential equations with constant coefficients, which are homogeneous. To solve an equation like this, we need to find two linearly independent solutions. If the roots of the characteristic equation are different real numbers, then we have the easiest case. The two functions that we want are e to the power r1t and e to the power r2t. If we have complex conjugates, lambda plus or minus I mu, then the two functions that we want are e to the power lambda t cos mu t and e to the power lambda sine mu t. And now we've just seen what to do if we have repeated roots. We have repeated roots, then the two functions that we want are e to the power r1t and t e to the power r1t. Let's move on to a different topic. I want to talk about reduction of order, and that's an extension of what we've talked about so far today. Let's suppose we want to consider y double prime plus pty prime plus qty is equal to 0. And suppose that we already know one solution to this differential equation. To be able to write down the general solution to this linear second order equation, we need to find the second linearly independent solution. So what can we do? The main idea in this section, something you've seen already today, is we're going to make a guess. We're going to guess that y2 is equal to vt multiplied by y1 of t. For some non-constant function vt. If we can find vt, then we have our y2. And if we have our y2, then we can write down the general solution to this second order linear equation. So let's do what we did before. We'll start with y2 is equal to vy1, differentiate 2 times. y2 prime would then be v prime y1 plus vy1 prime by the product rule, differentiate it again. We would expect to have 4 terms, but actually 2 of them are the same. We can combine 2 of them together as the middle term. y2 double prime is v double prime y1 plus 2 v prime y1 prime plus v y1 double prime. And then I want to put these into the differential equation. Like this. We need to rearrange this and we need to simplify this. Let's gather all of the v double primes first, and then I gather all the v prime terms, and then gather all the v terms. And let's look at the last bracket first of all. The last bracket is v multiplied by y1 double prime plus py1 prime plus qy1. But remember, we already know that y1 is a solution to this differential equation. So y1 double prime plus py1 prime plus qy1, we already know is equal to 0. So we get v double prime y1 plus v prime multiplied by 2y1 prime plus py2. Okay, let's just talk about the equal to 0 first of all. When we do the method of reduction of order, we must always get a 0 here. We must always get a 0 v. Why? Because y1 solves the differential equation. It's okay to have v prime terms and v double prime terms in our equation, but we must not have any v terms left. And we must always get a 0 here. If you don't get a 0 here, if you get something else, then you know you've made a mistake in your calculation. Please remember that when you do reduction of order, you must always have a 0 just here. Now, this equation, v double prime y1 plus v prime 2y1 prime plus py1 equal to 0, is actually not a second order equation. This is actually a first order equation for v prime. To understand this, what we can do is we can do a substitution. We can replace every v prime by u. So u just here. And then instead of v double prime, we have u prime. Now you can see this is actually a first order equation. And we know how to solve first order equations. We spent a chapter talking about first order equations. If we can find u, then we can integrate it to find v. And if we know v, then we know y2. That explains the name of this method. Instead of having to solve a second order differential equation to find y2, we only need to solve a first order equation for u. That's why it's called reduction of order. We're reducing the problem we have to solve from a second order equation to a first order equation. Okay, so let's just recap or repeat what I was saying. To do reduction of order, step 1, we're going to guess that y2 is equal to v multiplied by y1. We're going to put this into a differential equation and we're going to find an equation for v. And remember, we must always get a 0 in front of the v terms. We can have v prime terms, we can have v double prime terms, but we must not have v terms left. Step 3, we're going to set u to be equal to v prime, and then step 4, we're going to find u. After we know u, we're going to integrate it to get v, and then as soon as we know v, we know that y2 is v multiplied by y1. Let's do an example. Given that y1 equal to 1 divided by t is a solution to this differential equation, find a linearly independent second solution. So we know what to do now. We're going to take y1 and we're going to multiply it by some unknown function v. Differentiate two terms. Here we are. And then we're going to put these into the differential equation. We're going to simplify it down and we're going to end up with an equation which includes perhaps v prime and perhaps v double prime terms. So first let's put these in. Let's rearrange it to gather all of the v double prime terms together, all of the v prime terms together, and all of the v terms together. And remember, we must always have 0v. This last bracket must always be equal to 0. So what do we have? We have plus 4 minus 3 minus 1, which is 0. Good. Probably no mistakes so far. If we don't get 0 here, then you know that you've made a mistake. So we're left with 0 is equal to 2t v double prime minus v prime. The next step is to do our substitution. We're going to replace v prime by u. And that will give us the differential equation that we need to solve. We need to solve 2t du dt minus u is equal to 0. This is a first order equation, and this is a first order equation which is both linear and separable. So we know two ways to solve this equation. We could solve this as a linear equation, or we could solve this as a separable equation. I choose to solve this as a separable equation. I'll do this very, very quickly because this should be revision for you. First, rearrange this so that all of the u terms are on the left and all of the t terms are on the right. If we can do this, if we can separate the variables like this, then we're allowed to integrate both sides. We end up with natural logarithm of absolute value of u is equal to half natural logarithm of absolute value of t plus a constant. Rearrange this, and we get u is some constant t e to the power of a half. I'll leave the constant in for the time being. We'll remove that later. After we know u, we can integrate it to find v. The integral of t to the power of a half is 2/3 t to the power 3/2. And then we get another constant. And then y2 must be v multiplied by y1. Take our function v and multiply it by t to the power minus a half. We end up with 2/3 c t to the power of a half plus k t to the power minus 1. This is a second solution, but we can do better. We can simplify this a little bit before we finish. To properly finish this problem, we should simplify this. The first thing to remember is that we're trying to find a solution which is linearly independent from y1. And our second term, that's k t to the power minus 1, is just a multiple of y1. We don't need this. How can we get rid of this? We could just choose k is equal to 0. So that simplifies us to y2 is 2/3 c t to the power of a half. And this is true for any value of c. We could choose whichever c is most convenient for us. Now, I like simple functions. I like simple numbers. How can I make this as easy as possible? I can make this easy for me if I choose the value of c to be 3/2. And then I'm left with y2 is t to the power of a half. And that is the answer to this problem. I'll leave it for you to check that t to the power minus 1 and t to the power of a half are linearly independent. In other words, I leave it for you to calculate the Wronskian of these two functions and to show that this is not always equal to 0. Let's do another one. Given that y1 equal to t solves this differential equation, find a second linearly independent solution y2. Another reduction of order question. So we do what we did before. We're going to take y1 and we're going to multiply it by some unknown function v. We'll differentiate this 2 times, and then we're going to substitute it into the differential equation. I'll leave this for you to check. Again, we should not have any v terms, and we don't. 2t minus 2t is 0. Good. I'll leave it for you to check that what we end up with is 0 is equal to t squared multiplied by t v double prime plus 4v prime. And because this must be true for all t, we can remove the t squared. Don't need to worry about that. And then we could do our substitution of u is equal to v prime. And we end up with the equation that we need to solve. T du dt plus 4u is equal to 0. Again, this is linear and this is separable. So you know how to solve this. Here's the calculation which solves it as a separable equation. I'll leave for you to check that there's no mistakes here, and you can check that the solution is u is equal to some constant c, t to the power minus 4. So let's just recap. We know that y1 is t, that's our first solution. We've done the substitution, v prime is equal to u, and now we've found that u is equal to c to the power minus 4. Integrate this to find v, minus a third c t to the power minus 3 plus k. And therefore y2 must be minus a third c t to the power minus 2 plus kt. Let's simplify this a little bit. Again, we can choose k is equal to 0 because we don't need this. We want a solution which is linearly independent from t. We don't need a constant multiplied by t. We don't need that at all, so k is equal to 0 is fine. And then we could ask what value of c will make this as easy as possible. We could choose c is equal to minus 3. And then we get the answer of this problem, which is t to the power minus 2. And we could stop there if we wanted to. That would be a good answer to an exam question. But because this is a lecture, I'm going to do a little bit more. Does t to the power minus 2 really solve the differential equation? I'm asking, have we made a mistake? So let's check this. Differentiate this 2 times, put it into the differential equation, and what do we have? We get equal to 0. So the answer is yes, it works. Are t and t to the power minus 2 linearly independent? How do we answer this? We answer this using the Wronskian. The Wronskian of these two functions is minus 3 t to the power minus 2. And this is not equal to 0 for all positive t, which is where the differential equation is defined. So therefore, y1 and y2 are linearly independent. So, of course, now we have a fundamental set of solutions, and we can use them to write down the general equation. Let's move on quickly. I want to talk about non-homogeneous equations. But before I do that, I'm going to take a 5 And let's continue. Now I want to start talking about non-homogeneous equations. It's non-homogeneous because instead of equal to 0, we have equal to some function g of t. If we replace the function gt by 0, we have an equation which is called the homogeneous equation corresponding to equation 5. The general solution to equation 5 can be written like this: c1y1 plus c2y2 plus capital Y, where y1 and y2 form a fundamental set of solutions to the homogeneous equation corresponding to 5. In other words, if our equation was equal to 0, then the general solution would just be c1y1 plus c2y2. To take care of, or to account for this extra equal to gt part of the equation, we need to add on another function which is called a particular solution to 5. That's any solution to the differential equation. So, to summarize, if I wanted to solve a non-homogeneous equation, L of y is equal to 0, equal to g, step 1 is find the general solution to the homogeneous equation corresponding to it. In other words, solve L of y is equal to 0. We need to find a particular solution. We need to find a solution, any solution to our non-homogeneous differential equation, L of y is equal to g. And then we're going to add these two functions together, 1 plus 2. How do we do step 2? We're actually going to study two methods which can be used to do step 2. We're going to study one method now, and then in the next lesson, we'll study the next method. The method that we're going to study today to do step 2 is called the method of undetermined coefficients. And the idea is this. Step 1, we're going to look at the function gt. We're going to see what type of function it is. What does it look like? And then step 2, we're going to make a guess, which includes some constants. And then we're going to try to find the constants. Let me do an example to show you what I mean. Find a particular solution to y double prime minus 3y prime minus 4y is equal to 3e to the power 2t. So we look at our function 3e to the power 2t, and we're going to make a guess. What does this look like? This looks like a number multiplied by e to the power 2t. So our guess is that the solution would be the same thing. This must also be some number multiplied by e to the power 2t. Probably not the same number, but same type of function. So instead of number e to the power 2t, we're going to guess number e to the power 2t for some constant a, which we haven't found yet. We try to find this number a, and we're going to see if our guess works. So we'll take capital Y as a e to the power 2t, and we'll differentiate it 2 times, and then we're going to put it into the differential equation. Let's see if we can find a. So I'm starting with what I want to be true. I want 3e to the power 2t to be equal to capital Y double prime minus 3 capital Y prime minus 4 capital Y. And I'm guessing that capital Y could be written like this. So substitute in and simplify. and we end up with minus 6a e to the power 2t. And we want that to be equal to 3e to the power 2t. So what value of a do we choose? We choose a is minus a half. And then we're done. Therefore, a particular solution to this differential equation is minus a half e to the power 2t. Let me repeat this idea. We look at our green function. We look at 3e to the power 2t. What type of function is it? It's a number multiplied by an exponential function. So we guess that our particular solution is the same type of function. We guess that we also have number multiplied by e to the power 2t. And then the work in the calculation is just to find out what number would it be. And most of the calculation on this slide is to find that a must be minus a half. And then we're done. I'll take another quick break. And let's continue. Let's do another example. Find a particular solution to y double prime minus 3y prime minus 4y is equal to 4t squared minus 1. So let's do the same thing. Let's look at the green function and ask, what type of function is this? This is a polynomial. This is a second degree polynomial. So it's reasonable to guess that our particular solution must also be a second degree polynomial. So the guess we're going to take is at squared plus bt plus c for some constants a, b, and c. I'll leave this example for you to finish. What you would need to do is you would need to differentiate 2 times, substitute it into the differential equation, and find the numbers a, b, and c. There is a new word on this slide, perhaps new for you, perhaps you've seen it before, the word ansatz. This means a mathematical guess. So we try the mathematical guess, at squared plus bt plus c. Another one. Find a particular solution to y double prime minus 3y prime minus 4y is equal to 2 sine t. So let's look at this function. It's a number multiplied by a sine function. So we might make a guess that our particular solution is also a number multiplied by a sine function. But I've written here this is our first guess. There's a clue here that something's not going to work here. So what do? We differentiate it 2 times, and then we substitute it into the differential equation. We end up with 2 sine t needs to be equal to minus 5a sine t minus 3a cos t. And we need that to be true for all t. Now on the left, it's 2 sine t plus 0 cos t, really. So I need 2 to be the same as minus 5a, and I need to have 0 is the same as minus 3a. But we can't solve this. This is an inconsistent linear system. It's not possible to find a constant a which satisfies both of these equations. So our first guess has failed. Why did it fail? It failed because when we differentiated sine, we also introduced cos. But we don't have a cos on the left. What we can do is we could start with both sine and cos terms. Differentiate 2 times and put into the differential equation. And we end up with 2 sine t on the left is minus 5a plus 3b sine t plus minus 3a minus 5t cos t. I'll leave you that for you to check. So the sine terms must be the same. Minus 5a plus 3b must be the same as 2. And the cos terms must be the same. Minus 3a minus 5b must be equal to 0 cos t on the left. And this is a linear system which is consistent. It's possible to solve this linear system. I'll leave it for you to check that we need to have a is minus 5 over 17 and b is 3 over 17. So therefore, the particular solution to this differential equation is minus 5 over 17 sine t plus 3 over 17 cos t. When you're doing this method, when you're trying to find a particular solution, remember that sine and cos are friends. They always go together. If you see either sine or cos in GT, then your ansatz needs to include both sine and cos. Likewise, if you see either shine or cosh there, then your ansatz needs to include both of them because shine and cosh always need to go together. Another example. Find a particular solution to y double prime minus 3y prime minus 4y is equal to minus 8 e to the power t cos 2t. What's our ansatz going to be? What do we have here? We have minus 8, that's just a number, and then an exponential function, and then a cos function. So our ansatz could be a number, and then an exponential function, and then a cos function. But remember what I just said, cos and sine always need to go together. Anytime we have a cos in an ansatz, we also need to have a sine in our ansatz. So we're going to use the ansatz a e to the power t cos 2t plus b e to the power t sine 2t. Let me just repeat that. Our function gt is number e to the t cos 2t. So ansatz needs to be number e to the power t cos 2t. And then because we're putting cos in, we must also have the same thing, but with sine instead of cos. So also plus a number e to the power t sine 2t. Okay, then we do just what we were doing before. Differentiate this function 2 times. This is a little bit more complicated. but here we are. And then substitute into the differential equation. And here it is. Again, I'm not going to talk about the details here. I'll leave this for you to double check at a later time. We have minus 8 e to the power t cos 2t on the left, and on the right, minus 10a minus 2b e to the power t cos 2t, plus 2a minus 10b e to the power t sine 2t. That gives us a linear system of two equations. 10a plus 2b is equal to a. I've just cancelled the minus signs out. And 2a minus 10b equal to 0. You know from linear algebra how to solve this. So I'm just going to tell you the answer. Please check that the solution is a is 10 over 13 and b is 2 over 13. And as soon as we know that, we've effectively finished the problem, because straight away we can write down that the particular solution is 10 over 13 e to the power t cos 2t plus 2 over 13 e to the power t sine 2t. Now a theorem, because we have linear equations, if we know that y1 solves this equation, a y double prime plus by prime plus cy is equal to g1, and if we know that y2 solves the same differential equation but with g2 instead of g1, then when we added them together, we would end up with a solution to ay double prime plus by prime plus cy is equal to g1 plus g2. We can use this fact to solve this problem. Find a particular solution to y double prime minus 3y prime minus 4y is equal to 3e to the power 2t plus 2 sine t minus 8e to the power t cos 2t. Because we can break this up into 3 easier problems. A green problem, an orange problem, and a blue problem. These ones we've just done. We've done these already today. We already know particular solutions to these 3 differential equations. So by the theorem, all we do is we add our solutions together. This green function, minus a half e to the power 2, was a particular solution to the green differential equation. The orange function, minus 5 over 17 sine t plus 3 over 17 cos 2t is a particular solution to the orange equation. And this blue function, we've just did this in the previous example, 10 over 13 e to the power t cos 2t plus 2 over 13 e to the t sine 2t is a particular solution to the blue differential equation. Add them together and we end up with a particular solution to equation 7. So to find a particular solution to a y double prime plus by prime plus cy is equal to gt, what we've been doing is we've been looking at gt and then we're choosing a similar function for our ansatz capital Y of t. This method doesn't always work. There's one difficulty that can occur, as we're going to see in the next example. Find a particular solution to y double prime plus 4y is equal to 3 cos 2t. So let's do what we were doing before. Let's look at the function 3 cos 2t. That's number multiplied by a cos function. So our ansatz makes sense that it could be a number multiplied by a cos function. And anytime we have cos, we must also have sine. So also plus number multiplied by a sine function. And you'll see that again, I've written first guess here. Again, that's a clue that something's going to go wrong here and we're going to need to try again. Differentiate 2 times and substitute into the differential equation. And we end up with 3 cos 2t is equal to 0. And we need to choose A and B, so this is true for all t. But we can't. This is a failure. It's not possible to choose A and B to make this true for all t. Why did this happen? Why did our usual method not work? To understand this, let's solve the homogeneous corresponding to our differential equation. Take our differential equation and replace gt by 0. We get y double prime plus 4y is equal to 0. The characteristic equation is r squared plus 4 is equal to 0. And the roots are plus or minus 2i. So the general solution to the homogeneous equation must be c1 cos 2t plus constant sine 2t. That's why we got equal to 0 when we tried to use that ansatz. Because cos 2t and sine 2t appear in the general solution to the homogeneous equation, the rule is we cannot use the same functions. We cannot use cos 2t and sine 2t in an ansatz for a particular solution. So what do we do? If in doubt, multiply by t. We need two functions which, when we differentiate them, we end up with cos 2t and sine 2t terms. And perhaps other terms as well. What we're going to do is we're going to try to use t cos 2t and t sine 2t. Why? Because when we differentiate these two functions, we do get cos 2t and sine 2t terms, and some extra terms. We hope that the extra terms will cancel. So, second guess. Now I want to guess that the particular solution is at cos 2t plus bt sine 2t. That's the previous guess, but multiplied by t. Differentiate it 2 times, substitute into the differential equation. And what do we get? We end up with 3 cos 2t is equal to 4b cos 2t minus 4a sine 2t. Because all of the terms involving the extra t will cancel. And we can find A and B which satisfy this for all t. We can solve minus 4a is equal to 0 and 4b is equal to 3. So a particular solution to the differential equation must be 3 over 4 t sine 2t. So to recap, In your ansatz for a particular solution, you can't use exactly the same functions that you would use in a general solution to the homogeneous equation. Instead, you need to multiply them by t. That's the end of today's lesson. We'll do more examples next time. Chapter 3.8, sorry, section 3.8, we're going to be solving some initial value problems. We're going to be using the method of undetermined coefficients. Section 3.9, we're going to look at the other method to find a particular solution. That's the method of variation of parameters. And then finally, in section 3.10, we're going to extend out our ideas to higher order linear differential equations. Are there any questions?